Continuing on with our study of polynomial functions, the definition of a polynomial function is a little bit scary looking. The important things to note about the polynomials is that the exponents on the variable are these nice positive integer values like 4 and 2 and 1 and x to the 0. The coefficients of each of these terms are real numbers. The degree of a polynomial is the largest exponent, and the leading coefficient of the polynomial is the coefficient of the term with the largest exponent. It's a good idea to always write polynomials in standard form with the highest degrees first and then working your way down to the constants. Graphs of polynomials are these nice smooth continuous curves. They'll be real important to you when you get into calculus. And we're going to look at first today is what we call the far left and far right behavior of a polynomial graph. So it's what the graph does as x gets really big and very small. So as it goes off to the right and as it goes off to the left. And that's going to be determined by the leading term of the polynomial. So we're going to need to pay attention to the leading coefficient and the degree of the polynomial. We're real familiar with parabolas, ax squared plus bx plus c, which are what we call second degree polynomial functions because of the largest exponent being the 2. This is what we call an even degree since 2 is an even number. And remember what the graphs of parabolas look like. If the leading coefficient a is positive, we get a graph that goes up to the right and up as you go off to the left. And if the leading coefficient is negative, it goes down to the right and down to the left. If you're familiar with cubic functions, something like a times x cubed, this would be an odd degree, since the degree of it's going to be 3, an odd number. And the graph of x cubed, if the leading coefficient is a positive 1, is going to be increasing as we go to the right and decreasing as we go to the left. And if we look at negative x cubed, it's increasing on the left and decreasing on the right. There's different ways of saying this. A formal definition that you're going to see a lot of if you go on to calculus is as x approaches infinity, y approaches infinity, would be describing what's happening here as x gets big, y gets big, whereas as x goes off to negative infinity, y goes off to negative infinity also. So as we go off here to the left, y is decreasing, approaching negative infinity. So whichever notation makes the most sense to you. As x increases, y decreases. If you like to do it in words or symbols, just as long as you're being clear. Okay, so why is this important? If we take a look at this cubic here, negative x cubed, from what we saw in the previous slide, we would expect it to be increasing off to the left and decreasing as we go to the right. But if you graph this on your calculator using the standard window, negative 10 to 10, negative 10 to 10, you're going to see something that looks like a skinny parabola. But if you change the window, let x go from negative 10 to 30, and y go from negative 100 to positive 900, then we're going to see the graph that we'd expect to see from a negative x cubed. How did I come up with that window? I knew what it should look like, and I just kept trying. Okay, here let's kind of lay out all the different rules. So if you only have to look at the leading term, if the leading coefficient, the number in front of the term, is positive, and the degree of the polynomial is even, so that would be an x squared, an x to the 4th, an x to the 6th, what's going to happen eventually for the graph is on the far right, the function will be increasing, and on the far left, the function will be increasing also. If you have that leading coefficient positive, but you have an odd degree polynomial, so x cubed, x to the 5th, x to the 7th, what we should see on the right is the function eventually increasing on the right and eventually decreasing on the left. Now, if the leading coefficient's negative, and it's an even degree, it'll be both decreasing on the left and right-hand sides, whereas with the odd degree, it'll be increasing on the left, decreasing on the right. And the function will have up to n minus 1 turns. So like with a parabola's degree 2, to subtract 1 would be 1 turn, and we see that with parabolas. They always have 1 turn as they go from increasing to decreasing or decreasing to increasing. So a couple examples here. P of x here, we're looking at 2x cubed plus blah, blah, blah. All we really care about here at this point is the leading coefficient and the degree. The leading coefficient is a positive 2, and the degree is an odd number 3. So on the left and the right, as expected, we see the functions increasing on the right, decreasing on the left. We also see 2 turns. 3 subtract 1, so it turns once here, and then turns again here. And then this one, x to the fourth, subtract 15x squared. Again, leading coefficient's positive 1. The degree is an even 4. And so both on the left and the right, we see it's increasing, and we're seeing 3 terms. The fourth degree polynomials will have at most 3 terms, but it could also have only 1 term. Okay, maximum minimums are also important points on a polynomial graph. Let's distinguish between absolute and local. On this one here, the x cubed, we do have a high point here, and we've got a low point here. But both of these are what we call local maximums and local minimums. Because looking at this function, this is a maximum here for this part of the graph, but eventually the graph keeps increasing to infinity, so the graph does reach higher values of y. So this is only what we call local maximum because it's not the highest point of the graph. This graph has no highest point. Same thing here at the local minimum. It's a low point of the graph, but eventually the graph does go lower off here to the left as it approaches negative infinity. On this one here, the fourth degree polynomial, we've got a local minimum here, because again, in this restricted domain, it's a minimum, but it does go lower here. And this one is an absolute minimum because it is the lowest point of the graph. Okay, locating zeros. This is something that your calculator actually will do for you, but just give you a little bit of theory of what's happening behind here. So the idea is if you have a value a for a value of x, which we'll call a, that makes the function be negative, and another value for x we'll call b that makes the function positive, somewhere between a and b there must be a value x where the function actually equals 0. And we spend a lot of time looking for values of x that make the function equal 0. That's why we're talking about this. So I'm going to take a function here and I'm going to evaluate it at 1 and at 2. So first I'm evaluating it the old-fashioned way, plugging it in, calculating. And then I'm going to evaluate it using a remainder theorem from the last section. And the remainder of the function is what the function will equal when evaluated at 2. So at x equal 1, I've got a negative value. And at x equal 2, I've got a positive value. So somewhere between x equal 1 and x equals 2, there is a value of x that makes the function equal 0. Okay. And an interesting characteristic of polynomial graphs, if you can factor polynomial down, anywhere that we have a factor, we're going to have a 0 of a polynomial. So since x subtract 2 is a factor, at x equal 2, we have a 0 of the function. Since x plus 1 is a factor, oops, pointed to the wrong thing. There's the x equal 2, 0. Here's the x equal negative 1, 0. But notice that at x equal negative 1, the graph just touches, whereas at x equals 2, the graph passes through. Because we have this repeated factor, that's why it's just touching. If the x-intercept is a touch rather than a passing through, it's going to have a repeated factor. The factor is going to show up more than once. Here the x plus 1 is into the factored form twice, x plus 1 and x plus 1. Okay, one more thing. Even and odd powers, if it's odd, the graph will actually cross. If k is even, the graph will touch but not cross. If x subtract c is a factor of p of x k times. So here, this one, because it's to a power of 4, will just touch. At x plus 1, it will pass through.